What's up, y'all? Good morning. As you can see here, we're going to talk a little bit about forms of energy and how it does its thing. So, this will be a first little foray into this video lesson. Hopefully, it'll be good. Let me know your feedback later, please. But energy, all right? Check out in the background. You got a lot of different forms of energy you could see there. Maybe one obvious one, but there's a lot more that you probably don't recognize, and we'll talk about how that kind of all goes on in your daily life on a all the time basis. Okay, so first we're gonna say what is energy, and if you got our little anime Naruto Goku, whoever the heck that guy is, he is summoning all his energy in to destroy something, I'm sure. But what is energy anyway? Energy is the ability for something or someone to do work. So when you guys say, "Oh, I don't have any energy today," that's not the real definition of it. That's what you feel like doing what your mom and dad say or what we teachers ask you. So a little bit different. Energy in a scientific definition is the ability to do something. Could be an object on your table, could be your dog pulling a sled, could be you. Energy gets measured in joules, and I know that's a weird looking word, but joules is how you say it, and J is the whatchamacallit, the label, the label for it. So when you do a lot of math formula and they're calculating energy, they will use J for joules. There are going to be many forms of energy on this earth, and we'll talk about a few of them, but there's a lot more of energy forms than we will talk about today. Some of the most common forms of energy and the ones we'll talk about are mechanical energy, sound energy. You can probably guess what some of them are from some of these pictures up in here. Electromagnetic energy, chemical energy, and thermal energy, and one more, nuclear, your favorite. Everyone loves nuclear energy. So first we'll start with mechanical energy. Mechanical is kind of a sum of all energies kind of thing. So the definition of mechanical energy is the sum of an object's kinetic and potential energies. And you might say, well, what's kinetic or potential? Kinetic is anything that's in motion. So if I'm sitting here falling asleep and my hands are like my chest like this, I have a lot of potential energy in my hand, especially if there's other forms playing in part like gravity or something. Like if my computer's on my lap right now and I'm filming, if I fell asleep, it would have more potential energy than my hand on my chest because it has a higher probability of falling off due to gravity. So right now, if there's zero motion, it has 100% potential energy and zero kinetic. But as soon as it starts to move, it would switch from that 100 0 to like 90 10 80 20 30 70, bam, 100% in motion, and then it hit the ground again. It would go back to 0% kinetic, 100% potential. So that's what mechanical energy. It's often referred to as how work is able to be done. I don't know if you can kind of just think of it like that. Mechanical, I think machine, motion, movement. So the ability to do work, but it's always kind of a sum of kinetic and potential. When you think what's your potential, it's your ability to do something. And if you think of those words with kinetic in it, like what's that thing? The Xbox Kinect, that's a silly thing. I don't think they even have it anymore, but they put on your Xbox and it measured your motion. So if I wanted to ninja kick someone, it would move that and register my motion. So kinetic means in motion. Potential is not moving, it's stored. Some examples of this might be an energy a car has when it's moving, or books sitting on your desk, or you guys know I like to throw stuff in class. So in my hand, it's potential, 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 and as soon as I let it go, kinetic, 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 until it falls down on the ground. I'll have some examples of this later on some videos or something. Next is sound energy, and sound energy is a type of kinetic because it has to do with molecules in motion. It's a vibration of particles. So when anytime something makes a noise, and we'll play this animation over here. Whenever something makes, Hear that? Okay. So the noise vibrates. This could be like a speaker, and this right here is the vibrating of the speaker film back and forth. And when it does that, it hits the particles in the air, and the other particles hit other particles. I don't know why it's laggy like that, but you can see it makes waves. So it flies this way, it flies that way, and that's how sound radiates out in all different directions. And some of the things I like to think about when I look at this is when you go to a movie theater, if you look around on the walls and stuff like that, what do they got on that? They got drapes, they got carpets, they got like that egg cartony stuff. Because guess what it's supposed to do with the walls? Look at these. See this thing come over here? What happens to the particles when it reaches the wall? Let me play it one more time. Here over here first. It comes over here. Those particles hit, and some of them come backwards. So that's called like reverberation off the wall. So they pad that stuff so it absorbs the energy. So next time you're in the movie theater, hopefully when we don't have this stinking COVID going around, you can look and notice that and say that absorbs sound energy. Our ears detect the tiny vibrations that travel through air particles to our ears. So those little dots right there come in and hit in there, and you know the parts of your ear from when you were in elementary school or in that you have your eardrum and the hammer and all that. It hits that stuff and it vibrates, just like this kind of line here from the speaker. Sound cannot travel through empty space. And that's simply because there's no air in space. So if you think there's none of these particles, maybe these are oxygen particles, maybe these are helium, maybe these are hydrogen up in the air, nitrogen. There's none of that in space. So therefore, these waves cannot hit the particle and travel to the next particle and so on and so on. So that's why sound can't travel through space. It's pretty cool. Come on, baby. Electromagnetic energy is the second one. This is kind of the opposite of sound energy. Electromagnetic energy is not traveled through particles, but it travels through transmitted electromagnetic waves. So this right here is the electromagnetic spectrum. We'll talk about that in 1 second. It's a vibration of electrically charged particles, and they flow in this wave like this. It can travel through space because it does not need particles to move. So if you take a look at this sucker, is that the last one? I might have to come back. Okay. Types of EM waves, visible light. If you look here on the spectrum, this is the wavelength that visible light is seen at. So you can only see, like right here, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. That's the only wavelengths that our eyes can work and see. It's pretty crazy. Also, you have down here radio waves. They have the lowest frequency and the longest wavelength. A wavelength is how long it takes from getting the crest back to the crest. This is a trough. This is a crest. That's a wavelength, one wave. See how long that is? Longer. Down here, these have really short wavelengths. These are the more penetrating, stronger, scary waves for you guys. Low frequency means it doesn't come by very quickly, like frequent. If you frequent the store to get food during your COVID-19 quarantine, you're not doing the right thing. You're only supposed to go once in a while. So these have a low frequency of coming back around. These have a higher frequency because it comes back around quick. Okay, so radio waves, not very strong. They can go a long way. That's why we use them. They can't penetrate you and hurt you or anything like that. Microwaves, these are a weird one. They kind of have weird properties where they really are absorbed by fats and liquids. Okay, so what do we use microwaves for? To cook our food. And that's why when you put that stuff in the microwave, those things go in, they really concentrate on it, and it causes water and fats to excite the molecules inside really fast. So it does a really good job of cooking food. That's why you're not supposed to put metals and stuff in there, because it actually reflects it, and that can cause it to kind of reflect and explode instead of going into the thing. Not like in the flames, but it could break it. Infrared, right before we can see, the wavelength starts to get a little higher. Ultraviolet, after violet, so ultraviolet. Infra means less than, ultra means after, so after violet and Roy G. Biv. Then X-rays. You guys know these penetrate our bodies. UV too. Where's UV come from? The sun penetrates your skin, kills your cells, gives you sunburn. X-rays is like sunburn on steroids. If it goes into your get that stuff exposed to you, it can kill cells, can cause cancer. Gamma rays, you guys know that's even worse. So that's like instant from nuclear things, and you see like the Hulk and stuff like that. But so that's electromagnetic field and waves. It's pretty crazy, but this is a type of energy. Chemical energy is energy obtained from the breaking or rearranging of bonds in chemical compounds. So think about we did that physical and chemical changes stuff a while ago. This would be the chemical changes that we talked about in class, and we'll remind you of some of those in a second. You have to break or make chemical bonds, and that releases or absorbs energy. So some of the stuff we talked about in class was it is stored in food. So when I chew up my food, that's a physical change. But as soon as it goes down into our stomachs, that's chemical because it breaks the bonds of the food in the atomic level and it releases chemical energy. When we do the match, remember when I lit the match and you guys saw the different chemical changes, symbols coming up? Same thing. Those any kind of chemical reaction, there's going to be chemical energy release. So if we look at this match over here, we can see chemical changes. We have smoke, we have fire. You can hear the sound. It's a chemical change because you can't go back to this tipped part of the match. So that's a chemical reaction. That's chemical energy being released along with other things like light energy, sound energy, thermal energy, uh, all this stuff. And I like this because as soon as I start lighting my match, I can toast my marshmallows and ooh, gonna enjoy a nice s'more, and then it goes down, and you can finish that chemical energy transformation in your tummy, and we'll stop there. Thermal energy. Thermal, therm, the prefix therm means heat. So, an energy an object has due to the motion of its molecules. If you think about it, when it's a solid and it's frozen or water, the molecules are really slow. But when you add thermal energy, they start to get faster and faster and faster, and they quicken up because the energy increases. The faster the molecules move, the more thermal energy it has. Heat travels from higher energy to lower. So if we look at this GIF right here, this is supposed to be a metal rod, okay? And this is where your hand's holding the rod and you're sticking it into the fire, just being silly. But you can see it starts to get hot, and this is really dark red. And it'll start transferring the red hotter, and it creeps up, okay? And it creeps up, and this is how it conducts into your hand because metals are good conductors of heat and electricity. But that fire is going to excite the particles more and more until they hit the next particles, and they hit the next particles, and then boom, it's in your hand. And at first you're like, ooh, it's getting hot, and then you're like, oh, gotta drop that bad boy. Nuclear energy, last one. So nuclear is pretty cool. We talked about this in chemistry a little bit, but all atoms have nuclear energy in them because it's stored in their nucleus. And it could be a small atom like helium or hydrogen. They have it too, but those are generally more stable. Remember, we have that word isotopes. That mean the nucleus is a little different size. When the nucleus is a different size, it's unstable, so they will decay and release energy easier. When an atom's nucleus breaks apart or is joined, it's going to release energy. Unstable atoms like radium are radioactive and then they decay. So this is a radium atom right here. Has atomic mass of 222, 86 protons, but it is unstable. It's already radioactive. So when it's unstable, its nucleus is just too fat. It can't hold it. Boom, it'll decay this little particle of helium out, and remember it's atomic mass of 4, protons 2. If you subtract that from that, you get this numbers right here, and this means radium decays into a daughter isotope of polonium. But it's not radioactive at that point, and this helium splits off, so it's split from 1 into 2 things, but that releases energy. And this happens constantly in the sun. Okay, you probably knew that. The sun is got tons of hydrogen atoms combining, and it makes helium, and that's called fusion because it fuses them together. And this would be what happens in a hydrogen bomb. So hydrogen bomb is one where they smash the hydrogen atoms together and they mix it with explosives, and boom, you get a boom hydrogen bomb. This one up here would be an atomic bomb. It's different than the hydrogen bomb because it is fission. Which fission is not to combine, but to release, and that takes a lot of energy too. And they mix that, and then boom, you got tons of explosives. All right. So last slide. No, maybe not. Any and all these types of energies can change from one form into another. They can go from one to another, back and forth, all that stuff. Often, one form of energy can change into more than one form. Think about that match. Okay, the match started off as potential energy right there. I strike it and friction on a box or whatever, and it changes from potential to kinetic and thermal and light and sound and chemical and all those things. So one in the many. This brings us to one of the main points we want to talk about is law of conservation of energy. And I say here, does this sound familiar to you? Because it should. Law of conservation, and conserve means to save. So conservation of energy. And remember, we had law of conservation of matter. Energy cannot be created or destroyed. It can only change form. Law of conservation of matter was matter cannot be created or destroyed. It can only change form. So there's this whole veil of energy on our planet that just changes from form to form to form. It doesn't escape or get destroyed or created. It's here. It's pretty neat when you think about it, but that's what the law of conservation of energy is. So, for example, if 100% of one energy changes to others, it'll always equal 100 in some way or form as it gets pushed around our universe. So maybe it starts as 100, and something happens and it goes changes to 50% thermal, 20% sound, 15% light, 15% chemical. But this could be a good example of, hopefully we'll get to go out and celebrate this when it turns July. Fireworks. Boom. Okay, so just a quick little go around. You can watch this over and over if you want. We can talk about it. Emails, we'll have office hours and whatnot, but this will, we're going to do an activity where you guys do a roller coaster, I think, and you have to work on how to do kinetic and potential energies to balance it out and make it successful. But hope you have a good day. This is the maiden voyage of Yule on computer, so hope it was good. We'll talk to you guys on the flip side.